Hello everyone. In this video, we'll be solving problems on finding the dipole moment of different systems. Okay. So the first one is this. Uh, you have 4 point charges, as you can see. You have 4 point charges: Q, minus 3Q, minus 2Q, and 4Q, and they are placed at the four corners of a square, and you can see the distance separations between each of these charges. You're supposed to find the dipole moment of this system. Now, first of all, you can see that the net charge on the system is 0. See, the negative charge is minus 5Q and the positive charge is again plus 5Q. So the net charge is 0. Now, in this case, however, it would be a little difficult to separate the positive dipoles and the negative dipoles and find the net dipole. So we'll go by the definition of dipole moment, that is the sum of charge and position vectors. Okay, so the sum of the product of charge and position vectors. So let's say that this is the x-axis. Let me just call this as the x-axis, and this is the y-axis. Okay, this is the x-axis and this is the y-axis. Now we'll just write the charges and their coordinates. So we'll start with plus q. What's the coordinates of plus q? It is, as you can see, a comma 0. So its position vector is going to be a. I'm sorry. It is 0 comma 0 comma a. So it is simply going to be a j cap. For minus 2q, it is a comma 0. Hence, its position vector is going to be a I cap. For minus 3q, the coordinates is 0 comma minus a. Hence, the position vector would be minus a j cap. And for plus 4q, it is minus a comma 0. Hence, the position vector is going to be minus a I cap. Okay. So the dipole moment is simply p vector is equal to charge multiplied by its position vector. So plus q times a j cap plus minus 2q times a I cap plus minus 3q times minus a j cap plus 4q times minus a I cap. Okay, don't get confused. This is I cap. All right. So let's calculate this. What do we get? This is qa j cap plus, sorry, minus 2qa I cap plus 3qa j cap minus 4qa I cap. All right. So this is going to be minus 6qa I cap plus 4qa j cap. So that is our dipole moment. Hope you understood this. All right. So in this problem, we are supposed to find the dipole moment of a rod of length L. Half of it is charged positively and the rest half is negatively charged. All right. So the best way to do that is we can assume that all the positive charge is concentrated at the center of charge. All right. Let's call that plus Q. And all the negative charge is concentrated at its center of charge. All right, let's call that minus q. Now center of charge of the positive part would be at the center of the positive part. You can see that this is a very simple case, and that of the negative charge would be at its center. All right, so what is the separation what is the separation between these two. So you can see that the separation is actually L by 2, L by 4 plus L by 4. And the dipole moment would be from negative to positive. So this distance is L by 2. All right. So first of all, let's calculate the value of this Q. Q is simply going to be lambda times L by 2, and hence dipole moment here is simply Q times L by 2. Therefore, the dipole moment is going to be lambda L squared by 4. So that is your answer. That is the dipole moment of this particular system. I hope you understood this. Now, in this case, similar to the previous one, we are supposed to calculate the dipole moment. Now here we have a disk of radius r. Half of it is positively charged while half of it is negatively charged. We'll use the same strategy again. Let's say that the positive charge is concentrated at its positive center, while the negative charge is concentrated at its negative center. All right. And we'll say that the total negative charge is minus q, while the total positive charge is plus q. All right. So first of all, let's just calculate the value of q. So q is going to be charge density, which is sigma times the area. So what is the area of this semicircle? Semicircle's area is going to be pi r square by 2. That is the charge. Now, you know that for a semicircular disk, the position of the center of charge, or if you usually remember the position of the center of mass, so it's the same. That is going to be 4r over 3 pi. All right, 4r over 3 pi. So what is the total distance? The total distance is going to be 2 times 4r by 3 pi. So hence we can say that the dipole moment is simply q times 2 times 4r by 3 pi, because that's the distance between both the center of charges, positive and negative. And you can also see that the direction of this dipole moment would be upwards from negative to positive. All right. So dipole moment is sigma pi r square over 2 into 2 into 4r by 3 pi. And so the dipole moment is going to be, you can see that 2 gets cancelled, 2 gets cancelled, pi gets cancelled. So you'll have 4 sigma r cube by 3. That's the dipole moment. All right. Hope you understood this. Okay, here we have a non-uniformly charged disk, non-uniformly charged ring. The linear charge density, see, a thin non-conducting ring of radius r has a linear charge density lambda, which is equal to lambda naught cos theta, where lambda naught is the value of lambda at theta is equal to 0. So here we have a lambda naught charge density, while as you move up, the lambda changes by with this function. Lambda is equal to lambda naught cos theta. All right. Now find the electric dipole moment of this charge distribution. This is non-uniform. Okay. So we'll go by the basics. Let's just break this ring into small parts. So let's take a section here. Let's say we take a section here. All right. And this particular section, it subtends an angle d theta at the center. It subtends an angle d theta at the center. Now, dipole moment is simply going to be integral dq times r vector. That's the definition of dipole moment, right? For a continuous charge distribution. So let's write the values of dq and r vector. So what is dq? dq is going to be equal to lambda r d theta, because the arc length here is going to be r d theta. All right. So lambda times r d theta, or you could say lambda naught r cos theta d theta. That is the value of dq. Now what about r vector? What's the position vector of this particular element? The position vector, as you can see, is clearly r cos theta I cap, the component along this direction. Okay, well, I should have said that. Let's say that this is the x direction while this is the y direction. Okay, so r cos theta I cap plus r sin theta j cap. Now plug in the values. What do you get? P vector is equal to integral lambda naught r cos theta d theta multiplied by r cos theta I cap plus r sin theta j cap. I can take the constants outside. It is going to be lambda naught r square. These are the constants. Integral cos square theta d theta I cap plus sin theta cos theta d theta j cap. Sorry, j cap. Now, what would be the limits? Just a moment. What would be the limits of this integration? Theta would be from 0 to 2 pi. You'll have to consider all the elements, right? So it is going to be from 0 to 2 pi. Now here you can clearly see that this sine theta cos theta can be written as sine 2 theta by 2, right? And that sine 2 theta by 2 for one complete cycle is going to be 0. This will turn out to be 0. So we just have to calculate this particular part. And what about cos square theta? What can you write about cos square theta? Cos square theta can be written as 1 plus cos 2 theta by 2. So this becomes lambda naught r squared times 1 plus cos 2 theta by 2 into d theta, integral from 0 to 2 pi I cap, right? And again, when you split these terms, you'll get lambda naught r square. You can take this 2 outside, lambda naught r square by 2. You'll get integral d theta from 0 to 2 pi plus integral cos 2 theta d theta, again from 0 to 2 pi. All right. Now, just like before, you can say that this turns out to be 0. All right. And the value of this is going to be simply 2 pi. Just plug in the value and you have the dipole moment P is, by the way, this is I cap. Dipole moment is going to be lambda naught pi r square, and the direction is going to be I cap. That is your answer. Okay.